Hi, today we're going to talk about conditional probabilities. So this is our fourth lesson in the probability chapter, and to help us get our point today, we're going to look at a little table of data about the Titanic disaster. What we're going to do is figure if that old saying, women and children first, really applied here. I have my calculator out because I think we might want to see these probabilities in decimal form. It'll help us compare them a little bit better. But according to the table, what's our probability of being a female on this boat? Well, there were 470 females out of the 2,201 passengers that were registered. That's about, I think it's more than that, 2201. So around, and I always take my probabilities to 4 decimal places, 2135. So there is a 21.35% chance that you are female if you're on that boat. Men vastly outnumbered women, that's for sure. In fact, to find the probability that you were a male on that ship, we could go 1,731 divided by, or we could just say, hey, it's the rest of them, and that would be the complement of being a female, so 1 minus 0.2135. That's probably the easier calculation to make, and that is right about 7865.7865. Alright, let's look at it from the other perspective. The probability that you were a passenger who survived on the Titanic, 711 people survived, and that was out of the 2,201 who were on the ship. That's about a third. 711 divided by 2201. Yeah, 0.3230, about 0.3230, and we could do the didn't survive the same way that we did before, or we could just say, okay, the 1,490 people who did not survive divided by that 2,201. Either way, we'll come up with the same value, and that's about 6770, right around 2/3. Tragic. I think a lot of times we forget just how many folks did not survive that trip, and it's really sad. Today's lesson, however, is about conditional probabilities. These are all what I would call straight probabilities, one event. Okay? A conditional probability involves more than one event. In fact, we're going to ask or try and answer this question: what's the probability? Remember, we want to know if women and children really survived in a greater rate. So what's the probability that you did survive? That's what the yes is, given you are a female. Now that word given, I often use the word if in its place. So this is saying, what's the probability that you survived if you were female? Folks, we're only going from these females right now. We only care about them. So the bottom of our fraction is going to be 470, because all we're caring about are those females. Now, the number of them that survived were 344, and that looks like about 3/4. So let's divide 344 divided by 470. Yeah, that's about 0.7319. The probability that you survived given you were male, now we're looking here. The bottom of our fraction, we're only counting the males here, so the bottom of our fraction is 1731. Those that survived, only 367. Yeah, that's about, oh, that's terrible. About a fifth, I think. 367 divided by 1731. Yeah, wow. Right around 21.2%, 2120. Oh, that is sad. Okay. But our discussion today is about the conditional probabilities, and you'll notice that we used the same procedure. It's just that when we were using this given terminology, we just weren't selecting from everybody anymore. We were only selecting from a specific group. And in the Titanic example that we just looked at, your probability of surviving was dependent, folks. Dependent. It depended on your gender. That is, you had a better chance of surviving if you were a female. Yeah, so they really did do women and children first. This kind of probability where more information, like being female, changes the chance of something happening is called a conditional probability. And in words, when we found the probability that a randomly selected person survived given that person was female, we limited the selection field, is what I say a lot of the time. We were choosing from less people. We limited the selection field. Okay? And in symbols, the way we would write that probability statement is this: the probability of A given, they use the bar for that, probability of A given B, or of course they could just use the word probability of A given B. And if it's me, sometimes if A if B. The formula for finding a probability like that goes this way. You want the probability that both things happened, A and B, divided by the probability that B happened. And if you think about that, folks, that divided by, see, that's what we're saying here. We're not dividing by everybody anymore. We're dividing by only the people who fit the B category. So we limit the selection field. Let's see how that works in a couple of examples here. It says that we should write a probability statement, then find the probability that on a single roll of a die you get a 2 if you rolled an even number. Okay, so if we're writing the statement, probability of 2 given we were even. And I would love to have you think about the math here. What's your probability of being 2 and being even? Well, your probability of being a 2 is 1/6, and 2 is even. So your probability of being 2 and even, that's what we have to have, 2 and even, divided by the probability of even. Your probability of being 2 and even, however, is 1/6. Your probability of being an even number, well, 1/2, because half the numbers on the dice are even, or you could write 3 of 6. To simplify the complex fraction, most of you will remember you flip the bottom and multiply, so you multiply by the reciprocal of the denominator, and that gets us 2/6, which is the same thing as 1/3. And I'm going to ask you to think here for just a minute. We said the other day that a lot of these things you could logic your way out of, and this is one, folks. The probability that on a single roll you get a 2 if you had an even number, there are 3 even numbers and 2 is just one of them, right? There are 3 evens and you wanted one of them. So 1/3, right? The formula works, but sometimes the logic works as well. Let's see if we can do the same thing for the event. Draw a queen from a shuffled deck of cards if you drew a face card. So we want queen given face card. And if you're not familiar with the deck of 52 cards, 52 in total, and there are faces are jacks, queens, and kings, each of them 4 at a time. So there are 12 face cards in total, and there are 4 queens, and 52 cards altogether. So our probability of drawing a queen if we drew a face card, or given we drew the face, formula says the probability that you got a queen and that you got a face, divide by the probability that you got a face card. And you know, the same thing is true here as was true up here. Your probability of getting a queen is 4 out of 52. And if you got a queen, you definitely had a face card. So the probability of being a queen and a face is 4/52. Okay? The probability of having or being a face card all by yourself is 12/52. And when we flip and multiply, 52 over 12. 52's cancel, and we're looking at 4/12 or 1/3. Again, the same logic applies. Queens are just one of 3 types of face cards. So 1/3 has to be that probability. See, the formula works, but sometimes it's a little cumbersome. In fact, you have to think hard about it sometimes. We're ready now to discuss a second type of conditional probability, and that is a rule for finding the probability that 2 events both happen, the probability of A happening and of B happening. A formula for this looks like this. The probability that A happens multiplied by the probability that B happens given A has happened. Okay, so we're going to use what we did before to help us define this new type of probability, and we're going to apply it to the Titanic information. So I brought it up here for you again. It says that we should find the probability that a randomly chosen passenger was both female and survived. So female and yes. According to the formula, that would be the same as the probability that you were a female multiplied by the probability that you survived if you were female. Okay, are we there? The probability of the first thing multiplied by the probability of the second if the first has happened. All right, so your probability of being a female on that ship was 470 out of the 2,201 passengers. We multiply that by your probability of having survived if you were a female. So we think, okay, we're only here. The bottom of our fraction, we're only choosing from females this time, and those who survived were 344. So we think to ourselves, I see canceling, and we're looking at 344 divided by 2,201. 344 divided by 2,201. That probability was about 0.1563. Ladies and gentlemen, I think it's important for us to stop here and say, when we did this before, we got like 3/4 of the females survived, right? That was a much higher probability than this. However, now we're saying, what is your probability of doing both things? Being a female, of which there were very few on this boat. So if a lot of very few survived, that's why this number is so low. There were lots and lots of men, way more males than females. So the two conditional probabilities, the given and the and, they're very similar. They look at the probabilities from a differing perspective. Okay? This one, your probability of being both female and surviving, you guys, if you're in a two-way table like this one, you could have answered that right from the table. The only people who fit both categories, out of all the people that were there, the only ones that fit both categories are those 344. Remember what we said about logicking your way through it. Here's another example. To be both female and have survived, it's only those people, 344 out of the whole number who sailed. So we've looked at two different kinds of conditional probabilities today. I'm going to ask you to get out there and you do that. You try as quickly as you can, and we'll talk about this more in school.